September 1942, Wright Field, Dayton, Ohio. The sprawling military installation hummed with the organized chaos of American industrial capacity transformed into war production. Rows of hangars stretching across the landscape housing laboratories and offices where military, engineers and scientists wrestled with the technical problems that stood between American victory and the grinding attrition of a two-front war. Over the previous 18 months, since America's entry into the conflict, a catastrophe had been unfolding across American airfields from coast to coast, a disaster made worse by its inexplicability and its refusal to yield to any conventional explanation that military leadership could apply. The Boeing B-17 flying fortress, the pride of American bomber aviation, and the weapon that military planners believed would carry the strategic bombing campaign that would eventually bring Germany to its knees, was crashing at an accelerating rate during landing operations, but nobody could understand why the crashes were happening with such regularity or what connected these seemingly random incidents that had claimed hundreds of aircraft and the lives of trained aircrew whose absence from operational squadrons directly reduced American bombing capability at the moment, when that capability was most needed. The brass demanded answers from aircraft designers, from maintenance personnel, from engineering specialists, from anyone who might plausibly explain how America's most sophisticated bomber could survive the deadliest air defense systems Nazi Germany possessed only to crash harmlessly on its own runways in conditions that would have been routine for any pilot with basic training. The official designation for these incidents was pilot error, a classification that flew in the face of the obvious reality that these were experienced aviators who had trained for thousands of hours and who understood their aircraft with the intimate knowledge that comes only from hundreds of flight operations. Yet somehow these professionals were suddenly and inexplicably converting their bombers' landing approaches into uncontrolled descents that ended in twisted metal and smoking wreckage that recovery teams had to collect piece by piece from burned-out shells that moments before had been functional aircraft worth millions of dollars and representing months of construction labor. On the morning of September 15, 1942, a young psychologist named Alphonse Chapanis arrived at Wright Field under orders to investigate the B-17 landing crashes, a youthful academic who had recently completed his doctorate at Yale University and who possessed a particular fascination with the interaction between human beings and mechanical systems, how people made decisions under pressure, how they responded to stimuli, and how their cognitive processes could fail under conditions of stress and fatigue that pushed them beyond their normal operational parameters. Chapanis had been commissioned a lieutenant in the United States Army Air Corps only months earlier. After his major, professor at Yale arranged an assignment to the Aeromedical C laboratory at Wright Field specifically to address user interface problems that were plaguing the expanding American bomber fleet, a laboratory that was itself new enough that the research psychologist position Chapanis was filling had never existed before in the military hierarchy, representing an acknowledgement that the problems confronting American aviation had transcended engineering expertise and entered the realm where the peculiarities of human perception and cognition demanded investigation by specialists trained in those disciplines. The scope of the catastrophe Chapanis found when he began his work was almost incomprehensible in its scale. Over 22 months of operations, between 1941 and 1943, American B-17s had experienced approximately 400 crashes during landing operations, a number so large that it appeared the aircraft itself had been designed with a fundamental flaw that manifested only during the most critical phase of flight, the approach and landing sequence when pilots were most focused on their primary task but also potentially most vulnerable to human error if the tools they were using to control their aircraft contained ambiguities or design decisions that forced them to make intuitive judgments based on incomplete sensory information. The losses represented not only aircraft valued at hundreds of thousands of dollars each, but also represented trained crews and irreplaceable industrial capacity that could have been directed against German targets rather than being lost to accidents that occurred in friendly territory under conditions of relative safety, where these losses served no strategic purpose and only degraded American military strength through the accumulation of unnecessary attrition. Japanese began his investigation with interviews of pilots who had survived crashes, sitting with these experienced aviators in quiet offices and listening to their recollections of the moments before their aircraft hit the ground, asking detailed questions about their mental state, their perception of what was happening, their awareness of what controls they were manipulating in the seconds before disaster struck. What emerged from these interviews was a pattern that was so consistent and so uniform that it could not possibly be random or coincidental. A pattern that spoke to something systematic about the environment in which these pilots were operating, rather than something that could be attributed to the carelessness or incompetence of individuals who had proven their competence through successful completion of hundreds of previous operations. Pilot after pilot described the same sequence of events. The approach to the airfield after returning from a bombing mission or from a routine training sortie, hours of flight consuming the pilot's physical and mental reserves, the decision to lower the aircraft's wing flaps to reduce airspeed as altitude decreased and the runway grew closer on the windscreen, the pilot reaching toward the control panel with the intention of manipulating the flap lever to create the aerodynamic drag that would slow the aircraft to landing speed, and then within seconds, the aircraft beginning to descend too rapidly, losing altitude faster than the pilot's control inputs could correct, the landing surface rising to meet the bomber with increasing velocity until the aircraft struck the tarmac with impact forces that exceeded the structural strength of the fuselage and gear. Japanese listened to these accounts with the trained ear of someone whose academic specialty was human factors, someone who understood that when multiple trained individuals made identical mistakes in identical circumstances, the explanation rarely lay in some character flaw shared by all of them, but rather in something about the environment or the tools they were using that created conditions favoring error. Japanese obtained permission to inspect the cockpit of a B-17 to examine in person the controls and displays that pilots interacted with during the transition from flight to landing, and what he found in the narrow space where pilots sat surrounded by the mechanical complexity of a four-engine heavy bomber would transform aviation safety forever and would establish a new field of human engineering that would extend far beyond aircraft design into every domain, where humans operated machines and tools. Standing in the B-17 cockpit with the aircraft cold and silent, Japanese located the landing gear control lever and the wing flap control lever, the two devices that pilots manipulated during the critical landing phase, and he discovered something that seemed almost incomprehensibly obvious once it had been identified, but that designers had somehow overlooked. The two controls were virtually identical in shape and size, were positioned immediately adjacent to each other, separated by only inches, and appeared indistinguishable to a pilot operating under stress after hours of combat flying, during which his cognitive resources had been depleted by the constant demands of navigation, surveillance for enemy fighters, defensive maneuvering, and recovery from the adrenaline surge that combat operations produced. During the landing sequence, the pilot's hand would move toward the location where the flap control resided. But in the moments before landing, when visual attention was directed toward the runway and the altimeter and other instruments that displayed critical flight parameters, the pilot's proprioceptive sense of where his hand was in space and which lever his fingers were actually grasping could easily be defeated by the identical appearance of the two controls located in such close proximity that distinguishing between them required either direct visual confirmation or the ability to identify the correct lever by touch alone, a discrimination that the identical design of the two levers made impossible to accomplish reliably. Exhausted pilots, landing after 10 to 14 hours aloft during which they had absorbed flak damage from enemy anti-aircraft defenses and maneuvered to evade enemy fighters and struggled to maintain formation flying while dealing with the physical and psychological stress of knowing that their aircraft was carrying thousands of pounds of bombs and that every moment of flight brought cumulative risk of catastrophic failure, could reach for what they believed to be the wing flap control, only to discover too late that their hand had grasped the landing gear lever and that they had inadvertently retracted the aircraft's wheels before the aircraft had touched the runway, an action that would result in the propeller striking the ground at landing speed, with forces that would destroy the engines and render the aircraft as a smoking wreck. Once Japanese had identified the root cause of the crashes, a problem that lay not in pilot capabilities, but in aircraft design that failed to account for human limitations and human decision-making processes under conditions of stress and degraded cognitive resources. He set about developing a solution that would make it impossible for even an exhausted pilot to confuse one control for the other. Japanese knew from his academic training in psychology that humans could distinguish between objects by touch, even when visual confirmation was impossible. That the tactile properties of objects could encode information that the visual system might fail to detect under conditions of divided attention or stress. He proposed a simple but elegant solution that required no modification to the fundamental design of the aircraft and that could be implemented with materials that were readily available to maintenance and manufacturing personnel. Attach a small wheel-shaped knob to the landing gear control lever, creating a tactile discrimination that mimicked the circular shape of the landing gear itself, and attach a small wedge-shaped knob to the wing flap control lever, creating a shape that would feel distinctly different when grasped by a pilot's hand. The wheel shape would provide a mechanical memory aid that even an exhausted pilot's hand would recognize. The circular form triggering recognition not through conscious thought but through the automatic processes of motor, memory and sensory feedback that human bodies relied upon during high workload operations when the conscious mind was occupied with other demands. The implementation of Japanese solution was deceptively simple given the magnitude of its impact. Mechanics at airfields across the United States began attaching rubber-tired wheels to the landing gear control levers and small wedge-shaped covers to the wing flap controls, a modification that required only minutes to implement on each aircraft, but that immediately and dramatically reduced the frequency of landing crashes caused by control confusion. From the moment the first B-17s received these modifications, the pattern that had plagued American bomber aviation essentially disappeared. The 400 crashes that had occurred during 22 months of operations ceased to recur with any significant frequency, and trained pilots who had been blamed for making careless or incompetent errors were suddenly vindicated as the true cause of the crashes was revealed to be a failure of aircraft design rather than a failure of human capability or commitment. Japanese's intervention had accomplished what military leadership, aircraft designers, and training specialists had been unable to achieve through discipline, through increased training hours, through threats of court-martial or career-ending consequences. He had solved the problem not by demanding that humans change their behavior, but by recognizing that human cognition and human sensory perception operated within certain parameters, and that the proper response to human limitations was not punishment but rather the redesign of tools and interfaces to accommodate those limitations. The homemade solution that Japanese pioneered, the simple act of attaching different shaped objects to two identical controls, represented a fundamental shift in how humans thought about the relationship between people and machines, establishing the principle that would eventually be formalized as ergonomics or human factors engineering. The revolutionary concept that instead of asking humans to adapt themselves to the requirements of mechanical systems, designers should modify mechanical systems to accommodate the way humans actually thought and perceived and made decisions when operating under realistic conditions of stress and cognitive load. The success of Japanese's simple wheel and wedge solution immediately validated the revolutionary principle that would come to define 20th century engineering philosophy. Machines should be designed to accommodate human limitations rather than expecting humans to transcend their biological and cognitive constraints through discipline and training. By early 1943, the B-17 modification had been tested and approved for implementation across the American bomber fleet, and mechanics working in maintenance depots and on flight lines began installing the tactile discrimination devices that Japanese had designed, a process that required only minutes per aircraft, but that transformed the fundamental relationship between pilots and their machines. Word of the solution spread through airbases and maintenance facilities with remarkable speed, and the response from pilots was overwhelmingly positive. Veteran aviators and combat-experienced pilots expressing gratitude that someone had finally understood that the crashes were not the result of personal failings, but rather the inevitable consequence of asking human beings to maintain perfect discrimination between identical objects while operating under extreme stress and cognitive overload. The pattern that had plagued American aviation for nearly 2 years, approximately 400 crashes in 22 months, essentially disappeared once the control modifications became standard, installation on new production B-17s, and as existing aircraft in the fleet were retrofitted with the simple innovation. The human cost of this transformation was incalculable. Hundreds of lives saved from death and injury, hundreds of aircraft preserved from destruction, hundreds of trained pilots retained in service rather than being removed from combat rotations due to crash-related trauma or injuries sustained during landing accidents. The military brass that had been desperately demanding solutions suddenly discovered that the answer had not come from redesigning the aircraft's fundamental engineering or from implementing new training protocols or from subjecting pilots to new discipline measures, but rather from a young psychologist who understood that human cognition and human perception had certain immutable characteristics that needed to be accommodated rather than overcome. The recognition of Chapanis's achievement extended far beyond the immediate practical success of solving the B-17 crashes, because what he had essentially accomplished was the formal establishment of a new discipline that would come to be known as human factors engineering or ergonomics, a field of study dedicated to the principle that the proper design of tools and systems should begin not with what machines could theoretically do, but with what human beings could reliably do when operating under realistic conditions of stress, fatigue, and cognitive limitation. By 1945, as World War II drew toward its conclusion, and American military forces turned their attention to consolidating victory and preparing for the inevitable confrontation with the Soviet Union that would dominate the second half of the 20th century. The principles that Chapanis and his colleague Paul Fitts had developed through their investigation of B-17 crashes had already begun spreading to other military applications, from radar operator interfaces to weapons control systems to command center. Designs where the interface between human decision-makers and technical systems determined outcomes of potentially world historical significance. Fitts and his research team conducted a comprehensive analysis of 460 documented cases of pilot error, examining not only the B-17 crashes, but also instances of error in other aircraft types that shared similar design problems. And they published their findings in 1947 in a report titled Analysis of Factors Contributing to 460 Pilot Error Experiences in Operating Aircraft Controls, a document that would become foundational literature for the emerging discipline of human factors engineering, and that would establish a framework for thinking about the relationship between human beings and machines that would influence every subsequent generation of engineers and designers for the remainder of the 20th century and into the 21st century. The Fitts report went far beyond the specific problem of the B-17 landing gear and flap controls, developing a comprehensive taxonomy of control design principles that specified how controls should be standardized across aircraft types, how controls should be positioned to align with human intuitive expectations, how the shape and feel of controls could encode information that would guide operator behavior, even under conditions of high workload and stress that prevented conscious deliberation about what control to manipulate. Fitts articulated principles that seemed almost absurdly obvious in retrospect, but that nonetheless represented a revolutionary departure from the design philosophies that had dominated engineering practice for decades. Controls that performed opposite functions should look different. Controls that were operated in sequence should be arranged spatially to reflect that sequence. Controls and displays should be positioned to minimize the distance between them. Standardization across different aircraft types was superior to allowing each manufacturer to develop unique solutions because consistency reduced pilot error caused by moving between different aircraft types. These principles became codified in military specifications and eventually in civilian aviation regulations, establishing shape coding as a legal requirement for aircraft design such that Every commercial aircraft built after these standards were adopted incorporated. The lessons learned from Japanis's investigation of B-17 crashes into its fundamental design architecture. The impact of this transformation extended far beyond aviation, because the discipline of human factors that emerged from the B-17 investigation began spreading throughout American industry during the post-war period, influencing the design of industrial machinery, consumer products, medical devices, and every other category of human-machine interface, where the question of how human beings could be protected from their own cognitive and perceptual limitations through intelligent design became increasingly central to engineering practice. In 1949, Japanis published Applied Experimental Psychology, Human Factors in Engineering Design, widely recognized as the first comprehensive textbook dedicated to the systematic application of psychological research to engineering design problems, a work that would become required reading in engineering schools, and that would establish Japanis as the intellectual founder of a discipline that would eventually reshape how humans and machines interacted across every domain of modern technological civilization. The influence of human factors principles during the Cold War period proved decisive in multiple domains, where American technological systems competed against Soviet equivalents, and the consistent American superiority in human factors design and user interface considerations contributed substantially to American advantages in weapons systems, command and control systems, and strategic systems, where the quality of human-machine interface could determine outcomes of confrontation between the superpowers. Military strategists and systems engineers understood that providing American personnel with equipment that was intuitive to use and that minimized opportunities for operator error created decisive tactical and strategic advantages, and this understanding drove substantial investment in human factors research throughout the American military establishment during the decades following World War II, investment that produced not only more effective military systems, but also innovations that would eventually migrate to civilian applications. The commercial electronics and computing industries that emerged during the 1950s and 1960s discovered that many of the principles Japanis had developed for aircraft cockpits could be adapted to the design of consumer products and industrial equipment, and during a consulting relationship with Bell Laboratories that spanned 3 decades, Japanis applied human factors principles to the design of telephone systems and telephone interfaces that would eventually shape the standard keypad layout that became universal across all telephone technology, and that carries forward today on every smartphone and computing device used by billions of people around the world. In the 1950s, when Bell Labs was transitioning from rotary dial telephones to push-button telephone systems, Japanis and his colleagues conducted extensive research on human preferences for keypad arrangements, testing multiple configurations to determine which arrangement minimized typing errors and which layout felt most intuitive to users who had been trained on existing rotary dial systems but who would eventually transition to push-button technology. The research demonstrated that a 3x3 arrangement with the numeral 0 positioned below the 3, a configuration that aligned with intuitive expectations about how numbers should be arranged, produced significantly fewer operator errors than alternative arrangements that various telephone companies had experimented with. And this research led directly to the adoption of the standard keypad arrangement that remains virtually unchanged on every telephone, calculator and computer keyboard manufactured to the present day, a design decision that billions of people interact with multiple times daily without awareness that the arrangement they use was determined by psychological research conducted by Japanis and his colleagues decades earlier. The impact of this single design decision multiplied across the global telephone network and across all the derivative technologies that built upon telephone systems demonstrates the scope of human factors' influence on modern technological civilization. A few simple design principles rooted in understanding human cognition and perception became embedded in technology so fundamental and so universally adopted that the design principles themselves became invisible, integrated so completely into the everyday environment that most people using these technologies never conceived that alternative arrangements were possible or that the particular arrangement they encountered was the product of deliberate research into how human beings perceived and interacted with machines. By the 1960s and 1970s, the discipline of human factors had achieved sufficient maturity and institutional recognition that professional societies devoted to the field were established, including the Human Factor Society founded in 1957, now known as the Human Factors and Ergonomics Society, which grew from 90 attendees at its first annual meeting to thousands of members, representing the growing recognition across military, aerospace, industrial, and eventually consumer product sectors that designing for human capabilities and limitations was not an optional enhancement to engineering practice, but rather a foundational requirement for creating systems that functioned reliably and safely in the real-world environments where imperfect humans operated imperfect machines under conditions far different from the idealized laboratory conditions that designers often imagined. The tragedy of the 400 B-17 crashes had been transformed through Chapanis's insight and persistence into a foundation for a discipline that would save countless lives across multiple domains by preventing accidents caused by interface design failures rather than by human incompetence or carelessness. The specific shape-coding principle that emerged from his investigation of B-17 crashes became so fundamental that it was eventually incorporated into international aviation standards and regulations. And today, every commercial aircraft flying in the world operates with cockpit controls designed according to principles established by Chapanis's research more than 80 years earlier, a legacy that becomes even more profound when recognized that commercial aviation has become the safest form of transportation ever developed by human civilization, with modern commercial air travel characterized by safety statistics that would have been incomprehensible to those enduring the B-17 era when crashes were routine occurrences and aviation deaths numbered in the thousands annually. Modern aviation safety, recognized worldwide as the gold standard for safety-critical systems design, rests substantially on the foundation that Chapanis established during his investigation of B-17 crashes and the principles of human factors engineering that emerged from that work. Principles that influenced every subsequent decision about cockpit design, display arrangement, control placement, and pilot training throughout the evolution of commercial aviation from the jet age into the modern era of glass cockpits, fly-by-wire systems, and increasingly autonomous aircraft, where the interface between human pilots and sophisticated automation required even more sophisticated understanding of how humans perceived and interacted with complex systems. The discipline of human factors, born in emergency response to a crisis that threatened to undermine American strategic bombing capability during World War II, eventually transcended its military origins and became a defining characteristic of how modern technological civilization approached the design of systems ranging from consumer electronics to medical devices to infrastructure control systems, establishing through decades of accumulated research and practice that the most elegant and effective design solutions often came not from adding greater complexity, but from recognizing and accommodating human cognitive and perceptual limitations through thoughtful design that made intuitive behavior lead to correct outcomes, rather than requiring conscious deliberation or specialized training. The legacy of Alphonse Chapanis and Paul Fitts extends far beyond aviation, into every domain of modern technology where the question of human-machine interaction determines system performance and safety, and the principles they established in response to a wartime emergency have become so deeply embedded in contemporary engineering practice that they operate largely invisibly, shaping the design of systems that billions of people interact with daily without awareness. That the fundamental architecture reflects research conducted decades earlier by psychologists who understood that the road to safer, more effective and more usable technology lay not in demanding that humans change their nature, but in recognizing their nature and designing systems to align with the capabilities and limitations that define human cognition and perception. From the Boeing B-17 bombers that required simple homemade wheel and wedge knobs to prevent catastrophic crashes, to the modern smartphones and computing devices whose interfaces reflect the same fundamental principles of human factors that Japanis pioneered. The trajectory traces a transformation in how human civilization approaches the design of machines. From the older model that asked humans to adapt themselves to the requirements of machines through training and discipline and heroic effort, to the modern model that recognizes machines are tools created to serve human purposes, and that the quality of design should be measured not by the sophistication of the technology, but by how seamlessly and intuitively those tools can be used by ordinary people operating under ordinary conditions. That revolutionary insight, born in the desperate months when American bomber crews were dying in crashes that nobody understood, has become the foundation for how modern technological civilization creates the machines that define contemporary existence. A transformation initiated by a young psychologist's observation that identical controls co-located in close proximity created cognitive confusion that even well-trained pilots couldn't overcome, and whose solution, simple, rubber wheel and wedge-shaped knobs, established that the most powerful tool engineers possessed was not mathematical sophistication or mechanical complexity, but rather a deep understanding of human nature and human limitation applied with thoughtful purpose to the design of systems where human beings and machines intersected in their endless collaboration to accomplish the extraordinary feat of making human civilization increasingly safe, increasingly efficient, and increasingly aligned with the genuine needs and capabilities of the people whose lives those technologies supported and enhanced. The practical implementation of Japanis's principles extended far beyond military aviation during the post-war decades, eventually permeating every industrial sector and consumer technology market, with such completeness that contemporary users of smartphones, automobiles, medical equipment, and industrial control systems rarely appreciated how thoroughly their daily lives were governed by design decisions rooted in understanding human cognitive and perceptual limitations rather than machine capabilities. In 1955, when Japanis and John E. Carlin conducted their pivotal research at Bell Laboratories on telephone keypad design, they were grappling with a problem that seemed trivial on its surface, but that had profound implications for efficiency and user error. Across the emerging telecommunications infrastructure that was becoming central to American commerce and communication, telephone operators were making approximately 13% error rates when manually keying numbers into switching equipment, an error rate that meant that on average, 1 out of every 8 calls involved miscommunication or misdirection because the operator had struck the wrong button in a keypad interface that provided no tactile feedback and no visual organization that aligned with human intuitions about how numbers should be arranged. Japanis's team tested 6 different keypad configurations, ranging from 2 horizontal rows of 5 numbers each, the arrangement that existed at the time, to vertical arrangements and various configurations of the 3x3 grid that would eventually become standard, and through rigorous experimentation examining human performance metrics, they demonstrated definitively that the 3x3 arrangement with the 0, positioned separately below the grid, produced the lowest error rates and the fastest operator response times, metrics that aligned perfectly with human psychological preferences and perceptual organization, even though no explicit instruction or training was required to achieve superior performance with this configuration. The research that Japanis conducted on telephone keypads during the 1950s established a principle that would reshape consumer electronics design across the following decades. When interface design aligned with intuitive human mental models, and when tactile and visual properties of controls encoded information that users could process rapidly and unconsciously, performance improved and errors decreased automatically without requiring additional training or behavioral modification on the part of users. This principle, that would seem almost absurdly obvious in retrospect, was nonetheless revolutionary in an era when most engineers still believed that users should adapt themselves to whatever interface designers provided, rather than accepting responsibility for designing interfaces that accommodated user expectations and capabilities. In 1961, Japanis published Research Techniques in Human Engineering, a comprehensive volume that codified methods for conducting human factors research and that established standardized approaches for testing designs before implementation, a work that transformed human factors from an ad hoc problem-solving discipline into a rigorous science with recognized methodologies that could be taught, replicated, and systematically applied across different design domains. The influence of Chapanis's publications and research extended throughout American industry during the 1960s and 1970s, and companies like IBM, Xerox, and Bell Labs began investing substantially in human factors research teams that would work on interface design problems ranging from mainframe, computer control panels to office copier, interfaces to telecommunications switching equipment, all of these applications building directly on the principles Chapanis had pioneered while investigating B-17 crashes, the principle that machines should be designed for humans rather than expecting humans to adapt to machines. The Xerox Palo Alto Research Center, which emerged as one of the most prolific technology development institutions of the late 20th century, incorporated human factors principles from its founding in 1970, and the innovations that emerged from PARC, including the graphical user interface, the computer mouse, and networked computing systems, all reflected the influence of human factors, thinking on how people should interact with technology. The evolution of computer interface design throughout the 1980s and 1990s represented perhaps the clearest demonstration of how completely Chapanis's insights had transformed engineering philosophy as successive generations of personal computer manufacturers competed on the basis of user-friendliness and intuitiveness of interfaces, recognizing that the quality of human-machine interaction had become a decisive market factor that determined whether products succeeded or failed in the marketplace. The emergence of Apple Computer, under the philosophy that computing should be accessible to ordinary people with no special training, represented the culmination of a design approach that traced directly back to Chapanis's radical assertion that the engineer's responsibility was to design systems that accommodated human capabilities, rather than demanding that humans adapt themselves to system requirements. When Steve Jobs and his engineering teams at Apple designed the original Macintosh in the early 1980s, they incorporated fundamental human factors principles into every aspect of the user interface. From the design of the pointer and selection mechanisms, to the organization of visual information on the display screen, to the language used in menu systems and dialog boxes. All of these design decisions reflecting accumulated knowledge about human cognition and perception that Chapanis and his successors had developed through decades of research into how humans actually interacted with machines when operating under realistic conditions, rather than idealized laboratory circumstances. The iPhone that Apple released in 2007 represented perhaps the most comprehensive application of human factors principles to a consumer device in technological history, a product that achieved unprecedented market penetration by providing interface design that was so intuitive that users with no technological background could operate sophisticated computing and telecommunications functionality simply by observing physical and visual properties that encoded information about what actions were possible and what results would occur. The touchscreen interface of the iPhone embodied decades of human factors research into how humans perceived and manipulated virtual objects on display screens, how the location of controls on a display screen influenced user error rates and access speed, how visual organization of information aligned with human mental models of information organization, and how feedback mechanisms could be designed to communicate system status and response to user actions in ways that felt immediate and intuitive rather than requiring conscious interpretation. Today, more than 80 years after Alphonse Chapanis first identified identical landing gear and flap controls as the root cause of B-17 crashes, the principles he established have become so foundational to technological design that they operate almost invisibly, shaping interfaces and controls across every category of human-machine interaction, from the smartphones that over 5 billion people carry in their pockets and use for hours daily to the medical devices that monitor and sustain human life in hospital-intensive care units to the industrial control systems that manage infrastructure, ranging from power plants to water treatment facilities to telecommunications. networks that connect the contemporary world. The shape-coding principle that Japanese pioneered with rubber, wheels and wedge-shaped knobs attached to aircraft controls is now enshrined in international aviation regulations that specify exactly how landing gear and flap controls must be designed and differentiated to prevent pilot confusion. Regulations that remain in force because decades of data have demonstrated that shape-coded controls dramatically reduce the frequency of control selection. Errors even on modern glass, cockpit aircraft, where pilots interact with computerized displays rather than mechanical controls, proving that the fundamental principle transcends the specific technological instantiation and addresses something essential about how human beings process information and make decisions under stress and cognitive load. When pilots transition between different aircraft types, they rely on shape-coded controls that they can distinguish by touch and visual perception without conscious deliberation, and this standardization across different manufacturers and different aircraft types prevents errors that would otherwise arise from the cognitive load of learning new control configurations for each new aircraft. The principle has expanded far beyond aircraft into medical devices, where different medications or treatments are distinguished by color, shape, and tactile properties that make it virtually impossible for medical personnel to confuse one medication for another, even under the extreme stress and cognitive overload of emergency medical situations, where seconds of confusion could mean the difference between life and death. In modern hospitals, medication dispensing systems incorporate shape coding and color coding for different drug categories. Intravenous tubing for different medications uses different colored connectors that are shaped to prevent incorrect connections. And surgical instruments are designed with shape and tactile properties that guide correct usage even when surgeons are operating under time pressure and stress conditions where attention cannot be devoted to conscious problem-solving about which instrument should be used for which procedure. Designers of medical devices, informed by human factors research that traces back through decades to Japanese's work, recognize that the question is not whether medical personnel will be under stress during emergencies, or whether they will sometimes make cognitive errors, but rather how to design systems that minimize the opportunity for errors to occur by making correct actions. Intuitive and incorrect actions require conscious effort and deliberate violation of design intent. The taxi industry discovered through experience that the most reliable way to ensure that taxi drivers delivered passengers to the correct destinations was not to provide more training, but rather to replace paper address books and verbal instructions with GPS navigation systems that were designed according to human factors principles to provide information in ways that human drivers could perceive and act upon intuitively, guidance that felt natural and that aligned with existing mental models of how directions should be provided and how information should be presented during the demanding task of navigating urban traffic, while maintaining attention on vehicle operation and safety. Video game designers discovered that the most engaging and commercially successful games incorporated human factors principles throughout interface design, from the mapping of controller buttons to game actions that felt intuitive and natural to the organization of menus and information displays that aligned with player expectations to the feedback systems that communicated game state and player progress in ways that felt immediate and satisfying. Fitness trackers and personal health monitoring devices that billions of people now wear daily incorporate human factors research into how information about physical activity and health metrics should be presented to users in ways that are intuitive and that encourage engagement with personal health management behaviors. Design decisions that influence whether people use these devices consistently or abandon them because the interfaces are confusing or frustrating. Consumer product manufacturers ranging from kitchen appliance manufacturers to furniture designers to automobile manufacturers now employ human factors specialists as standard practice, recognizing that competitive advantage in mature markets often depends on interface quality and ease of use rather than on fundamental functional differences between competing products, a principle that traces directly back to Japanese's assertion that good design accommodated human capabilities rather than demanding human adaptation. The question that Chapanis posed in 1942 when he investigated B-17 crashes, not why pilots were making errors, but rather why the interface design made errors possible for competent pilots operating under realistic conditions, has become the central organizing principle for how contemporary technological civilization approaches design across every domain, from consumer electronics to industrial equipment to medical devices to infrastructure control systems. The answer that Chapanis discovered, that humans could distinguish objects by touch, and that shape and form could encode information that guided behavior more reliably than verbal instructions or abstract symbols, has expanded into a comprehensive discipline of human factors and ergonomics that informs every consequential design decision across modern technological civilization. Alphonse Chapanis passed away in 2002 at the age of 85. Having lived through the entire evolution of human factors, from an ad hoc problem-solving activity in a World War II emergency to an established discipline with professional societies, academic programs, standardized research methods, international conferences, and institutional presence in virtually every sector where human beings operated machines or systems of any complexity, his legacy extends through countless successors and students, including Paul Fitts, whose research on motor performance and cognitive load shaped how designers thought about the placement and design of controls, through generations of human factors, professionals who have applied Chapanis's principles to novel technological domains as technology evolved from mechanical systems to electronic systems to digital systems to the artificial intelligence and automation systems that are beginning to reshape human-machine interaction in the contemporary era. The problems that Chapanis identified in aircraft cockpits, that identical controls in close proximity, created confusion for competent operators. That visual attention to primary tasks could lead to errors in control selection when controls were not sufficiently differentiated, that stress and fatigue degraded cognitive resources for distinguishing between similar objects, remain relevant today in domains that would have been inconceivable to Chapanis in the 1940s, but that nonetheless present the identical fundamental challenge of designing systems that accommodate human capabilities and limitations rather than expecting humans to transcend their nature. The homemade tool that saved B-17 bombers from disaster, a simple rubber wheel and a wedge-shaped knob attached to aircraft controls, represents a profound insight into the nature of human-machine interaction that has become the foundation for how contemporary technological civilization designs every consequential system where human performance and safety determine outcomes. An insight born not from advanced mathematics or sophisticated engineering, but from a young psychologist's careful observation that good design begins not with what machines could do, but with understanding what humans could reliably do when operating under realistic conditions of stress and cognitive limitation.